Okay, so we are now going to start talking about antiderivatives. So the idea of an antiderivative is that we have a function and we're essentially going backwards. So instead of taking a derivative, we're trying to undo a derivative. And so, so the definition is going to be, let's see. That if we're given a function f of x, an antiderivative of f of x is going to be any function, and we usually use capitals to denote antiderivatives just to differentiate them from the function that we started with. So here, since we used f for our function, we'll use capital F for the antiderivative, such that, so any function, capital F, such that the derivative of capital F is equal to the function that we started with. Okay? So it's saying that we found a function that goes backwards or gives us the antiderivative, right? So undoing differentiation. Okay, so notice that I used the word an antiderivative, not the antiderivative. For any function, when we were taking derivatives, it had exactly one derivative. There was only one correct answer for that kind of problem. But with antiderivatives, these are not unique. You can have more than one antiderivative for one function. So we say that antiderivatives, try to write this, antiderivatives are not unique. Okay. But they are all very similar. They are not unique. You can't get exactly one, but they only differ by the addition of a constant. So for any antiderivative, capital F of our function f, if we take f and we add a constant c, then this is also an antiderivative of f. Okay, and to see this, let's look at a concrete example. So say we start with a function, so say x squared, or sorry, oops, I gave away the answer. So say we start with a function 2x, then an antiderivative of that would be capital F, I'll call this f1 because there's going to be another one, would be x squared. So you can check that if you were to take the derivative of x squared, it will give you 2x, and that is what makes this an antiderivative. Also, if we were to take another function, x squared plus 1, then if we take the derivative of this function, x squared plus 1, we also get 2x. And so the reason that we don't get uniqueness, but we get uniqueness up to this addition of a constant is because when we take a derivative, always the constant disappears. So when we're trying to go backwards, we don't have that information anymore. Once we take a derivative, the constant is gone. We don't know whether it was there, like in this case, the first function didn't have a constant, or if it did have a constant and we just don't know what it is anymore, right? So that's basically what makes these or so there's a little bit of ambiguity there. But these are both antiderivatives. This is derivatives of f. Okay. Now, as you can see, I have this table here. So we're going to go through and basically for all of the functions that we had derivatives for, our table of derivatives that you hopefully have memorized, we're going to have the opposite formulas for these, right? Okay, so starting off with the first one, if c is a constant, then the antiderivative of that will be c times x, right? So this is the most basic antiderivative. We're really just ignoring the fact that we could possibly have a constant added to this. So that's why in the title of this table I wrote an antiderivative, and really it's going to be the most basic one. So just without adding a constant. Okay. So this is an antiderivative of a constant. We just get c times x. If we have x to the power n, and it's really important that n is not equal to -1, then we have this sort of reverse power rule. So we do the power rule in reverse. So instead of subtracting 1 from the exponent, we add 1 to the exponent, so we get m plus 1, and then we have to account for when we take the power rule, we get that constant out front. We have to cancel that constant, so we have to also multiply this by 1 over n plus 1. Okay, so this is our antiderivative in this case. So you can just think of this as we add 1 to the exponent and divide by that new exponent. If you take the derivative, you can double check that this actually is an antiderivative of x to the n. So you would get n plus 1 over n plus 1, this one coming from the constant being out front, and then x to the n plus 1 minus 1. So you would end up with this just being 1 and getting just x to the n, right? And so I would actually encourage you when you're doing these, it can be really easy to get mixed up because we've been doing derivatives a lot up to this point, right? We've been using them a lot. And now all of a sudden you're having to go in reverse. And that can be confusing. So it's always a good idea, if you're not sure about your answer, to just take the derivative and double check that you get what you started with. So here we got x to the n. That is exactly what we wanted. And so we just confirm that that is the correct answer. Okay. Right, let me do an example of this. So this is just an example of using this rule. So on an actual function, let's say f of x equals x to the 5th, then the antiderivative will be x to the 6th, and then we have 1 over 6 as the constant out front. And you can double check that this would give you x to the 5th if you take the derivative. Another example, let's use g for this one, is, so we can also use this for fractional powers. We can use it in all of the cases that we use the power rule for, but except for that n equals -1. And so in this case, you will get x to the 3/4 plus 1, and then you will have 1 over 3/4 plus 1. And if we simplify this, we would get if you find a common denominator, you'll get 7 over 4. So 3/4 plus 1 simplifies to 7/4. And then you'll get 1 over 7 over 4. And then if we want to rewrite this without a complex fraction, we would just get 4/7 x to the 7/4. Now, for fractional powers, it's a little bit easier. You can go through this process, and it's not a wrong way to do it or anything like that, but it's a little bit easier and a little bit faster to think of it as, so here for fractional powers, you first add 1 to the exponent, and then multiply, so you'll get a fraction, right? Then you multiply it by the reciprocal of that power. So just to do a quick example, that way we would have, let's see, we've used FG, so let's use H, x to the 1/2. The antiderivative, or an antiderivative here, would be, well, we would add 1 to the exponent. That would give us 3/2, right? If we simplify, let's go ahead and do this in one step. So 1/2 plus 1 is 3/2, and then we multiply by the reciprocal of that, so it would be 2/3 out front. And so you see, you don't have to go through the process of simplifying it if you just remember that this is how it works for fractional powers. Okay, but we'll have plenty of practice with these. Now let's go through and fill in this chart. So as I said, this power rule does not work, or reverse power rule, however you want to think about it, does not work for n equal to -1. And that is because that when n equals -1, we get this case, and we know that the natural log of x is, the derivative is 1 over x. So we have to remember that in this specific case, we get the natural log of x. Now, we will always have absolute values on this, right? The reason being that we know that the derivative of natural log of x is equal to 1 over x. We also saw that the derivative of the natural log of the absolute value of x was equal to 1 over x. It just had a larger domain. This function has a larger domain than just the regular natural log, because this one is also defined on the negative half of the real line, right? So the reason why we always do this is because this will have the same domain as 1 over x, right? These functions will have the same domain, so we really want to use natural log of the absolute value of x, so don't forget that that has to be on there. Okay, now I'll just clean this up a little bit. Okay, now similar to the previous one, we have that this will be the antiderivative of, sorry, not natural log, but log base b of the absolute value of x. So we can do this for other logs, right? This is just straightforward, most basic antiderivative. E to the x is a simple one. We know that the derivative of e to the x is e to the x, so this is the easiest antiderivative as well. Similar to that, we get for b to the x, for some base b, we do get b to the x, but we have to divide by the natural log of b. I should probably move this up just a little bit so it fits. Great. So that is our antiderivative. Cosine of x, remember that the derivative of sine is cosine, so we get the antiderivative of sine, or cosine is sine. So be careful with these. It's easy to get the negatives, the signs of these mixed up. because now we're going backwards. So the antiderivative of sine is negative cosine. And this is really easy to mix up, so definitely when you're practicing doing these, I suggest that you take the derivative just to double check your answer. Okay, and now we have the rest of the trig functions. So this one is going to be tangent. Here we have secant, cotangent. Oh, sorry, I got this mixed up. Cosecant. Oh. And cotangent. There we go. So notice these are, at least these, maybe actually all four of these are just exactly the derivatives of these trig functions. Most of the time you won't see this exact form. I mean, you may, but these ones are really more useful, I would say. And then the others these are derivatives of the inverse trig functions. So we are just going to get as antiderivatives the inverse sine, inverse cosine, and inverse tangent. These are good to remember because they do look a little strange when you think of trying to find the antiderivative of this and it ends up being inverse sine. So just try to keep these in mind, that these are the antiderivatives of these last three. Okay, so in the next video we'll talk a little bit about a little bit more about antiderivatives and do some examples. Okay.